So we'll start the epipolar geometry. So as I briefly talked about, you can consider the two cameras here. This is camera 1 and this is camera 2. We call it O and O prime. These are the centers of the lenses. And then we have the image 1, the image of the scene in camera 1, and this is image 2, image of the scene in camera 2. And the line between O and O prime, that means if you draw a line from the center of the lens of your left eye to the center of the lens of your second eye, that's called the baseline. Baseline is about 5 centimeters for a human being, and that one you can see the baseline here. And we are considering a point in 3D. This is a 3D world. This is a 3D world, a point in the 3D world. So that point is somewhere, and if you want to find where that image of that point is in the first camera, that is O, what we need to do is we have to draw a light ray from that point. Yeah, these I'm drawing a wiggly line, light ray to the center of the camera, right? When that light ray cuts the image plane, that's where the image is, right here. So if you know capital X again, if you want to make an image on the second camera O prime, you draw a light ray from that 3D point X, cutting the image plane to the center of the second camera. So it cuts the image plane right here, that is the image. So you can see uh, when you have two cameras, the centers of the two cameras are defined, and when you keep a 3D point capital X, based on where that point is, you can draw a triangle joining that point and the two camera centers. And when those two rays cut the image plane, you have the image in the first camera right here and the image in the second camera, and there is a triangle. This triangle, you can see that. So that triangle is called epipolar plane. Epipolar plane. So we'll understand them in slightly more detail in the upcoming slides. So we'll once again look at the epipolar geometry setup, so-called epipolar constraint and essential matrix. When we know the intrinsic camera calibration matrix, that means capital K, that we studied before, we will have the essential matrix. And if we do not have the intrinsic camera calibration matrix, we will have the fundamental matrix. So they are important matrices. You can see the name given to that is also fundamental matrix. And then we briefly talk about the estimating of the fundamental matrix, although we will not do it in. Of course, you can use software to do that. Yeah. So let's look at this epipolar geometry setup, which I described earlier, step by step. Suppose we have two cameras with centers O and O prime. You can see the centers here, the camera center of the first camera and the second camera. You can see O and O prime. Yeah, over there. And then when we join them, we call it the baseline. So baseline is the line joining the camera centers. And epipoles are the places where the baseline cuts the image planes, epipoles, epipole E and epipole E prime. For the second camera things, we all use the prime symbol, right? Can you see that prime symbol? So then consider a point X, which is a 3D point. So because this is a 3D point, it will have an X coordinate, yeah? It will have a Y coordinate, and it will have a Z coordinate. And of course, we will put 1 there, right? This is how we designate these kind of points, right? Then we can consider the images. So this is that light ray that I described, that light ray going through the image plane and striking going through the center of the camera, starting from this capital X point. It's just a point, although it's drawn as a circle to make it visible. So this is where that light ray cuts the first image plane. That's where the image is made. And if we consider the second camera center, here is a light ray. I'm drawing a wiggly line. Not because I like wiggly lines. It is very difficult to draw straight lines. So this is the image of the same point in the second camera. So we designate them as X and X prime. I hope that also is clear to you. All right. And then this plane constructed between O prime and capital X. This is called the epipolar plane. For that particular 3D point and the two camera angles. So you can see when you move capital X up and down, this triangle also moves like that, right? Yeah. Uh, so that's why it's called, this is a family of planes passing through O and O prime. Family of planes passing through O and O prime. Because this O and O prime, this axis is fixed, this line is fixed, it's fixed, and then when you move capital X, this rotates. You can see that plane rotates about O and O prime. Yeah. Okay, so uh, what are epipolar lines? So epipolar line is the line along which the image plane is cut by the epipolar plane. The epipolar plane is a triangle, right? Triangle is the epipolar plane. So you can see that this grayish, beige colored one, this triangle is epipolar plane, and that epipolar plane cuts the first image plane right along this line. It's called epipolar line. So you can draw it, extend it like that. This is the epipolar line. And the triangle cuts the second image plane along this line. That's the second epipolar line. Yeah. So uh, equivalently, they are intersections of the epipolar plane with the image plane, thus they are coming in matching pairs. Epipolar lines connect the epipoles to the projection of X also. So you can see this epipole gets connected to the projection of capital X, and that's the epipolar line, this epipolar line. And this is the other epipolar line. And we call it actually L, and we call it L prime. This epipolar line L prime, obviously. Okay. So now the geometry, I hope, is clear to you. Polar plane, epipolar lines, the baseline, and the epipoles. Okay, these are some actual epipolar lines. Here you can see, now think about this point in the vase where these spheres of these characters are touching. And this is a different view of this. You can see this is image 1 taken from the camera 1, and this is image 2 taken from the camera 2. And you can see now these are, I'm telling you that these are matching epipolar lines. This epipolar line, that one, matches with this epipolar line, corresponding to the same 3D point. So therefore, you can see if you take a 3D point on that epipolar line, it actually appears in the other epipolar line. And you see that same there. So this same point, this point is on that epipolar line, corresponding epipolar line. Yeah, this same point is on the corresponding epipolar line. Okay, any questions about these things? I hope you can understand this. Yes, let's move forward then. Now, different kinds of camera configurations we can consider. First configuration is the two cameras are looking at the same scene. You keep a scene somewhere and two cameras are looking at the same scene. So this is that case. In that case, epipolar lines are there. The epipoles are finite. That means you can touch the epipole. That is not an infinite epipole. It may be visible in the image also. So if you actually draw the epipole lines, you will see they are crossing. So then this configuration is like you are keeping the camera pointed toward a mountain and you are traveling along the train. Motion parallel to the image plane. Where are the epipoles and what do the epipole lines look like? So what are the epipoles? Epipoles are the places where the OO prime cuts the image plane. Where do they cut? They cut at the infinity. So epipole lines are like that. Epipoles are at infinity. Yeah, right. And then the other one, okay, here is an example of that. You can see where do the epipolar lines meet? They meet at the infinity. That's why the epipoles E and epipole E prime are at infinity. E and E prime are at infinity. That's where these parallel lines meet. That is because you are traveling in a train with camera kept perpendicular, camera axis is perpendicular to the sea. Yeah, perpendicular direction of motion. Now this one, camera is moving along the optical axis, like so, right? Like so, when you're moving like so. That's what's the situation there. In that case, motion perpendicular to the image plane, epipole is the focus of expansion and coincides with the principal point of the camera. Principal point is the center of the image. And then you can see the epipoles are there, right? lines go out from the principal point. Okay, so now we have covered the epipolar geometry setup. Is there any question about the epipolar geometry setup? Okay, let's move forward. Please don't hesitate to ask a question if you have. Then now let's try to derive the epipolar constraint. All right. This is the part where you have to pay a little bit of attention. Suppose we observe a single point X in one image. All right. Now, the question is corresponding to this image X, there must be a point in 3D, in the 3D world. Where is that point? Where can that point be? So think about it. So that point can be anywhere along that light ray, right? Anywhere along that. That point can be here. That point can be here, here, anywhere along that ray. If there is a point, that will be imaged at this small x. Okay, that part is clear. Where can we find x prime corresponding to the x in the other image? That's the question we are asking. So now this one is defined, okay? Corresponding to that, capital X can be anywhere on this ray, right? Okay, now let's consider one point along the ray. Assume for now that we know that capital X is right here. Capital X is here, this point. That's our capital X. Assume that. Okay. If that is the case, how do you find its image? So what do? You join the camera center and this one, right? Like so. You join it. And where it cuts the image plane, you will have small x prime, right? Small x prime. That's how you do it. But see, you have to do that joining with this one, this one, this one, this one, anyone, right? So finally, what are the possible locations of capital X's image x prime? They will be on a line, right? They will be on a line. They will be on a line. That's the corresponding epipolar line. That line is the image of this ray, image of this light ray in this camera O prime. This is what we need to understand. Okay, so we will go through the slides. Again, this is possible, this is possible, this is possible. Yeah, this is possible. Yeah, what I did earlier. Okay. Where can we find x prime corresponding to the x in the other plane? Along the epipolar line corresponding to x. Projection of visual ray connecting O and x with the second image. In the second image. I hope it is clear to you. So this is the projection of that. This is the ray. This is the light ray. And what is the projection of that light ray? That means this triangle should cut this image plane. This is where the triangle cuts the image plane. So that is the epipolar line actually. It's a projection of the visual ray connecting O with X. I hope that this is clear. So this is the constraint that we need to encode. Similarly, all points on the left image corresponding to X prime have to lie along the epipolar line corresponding to X prime. So X prime, O prime, that defines a light ray. Image of that light ray is this line where that triangle cuts the image plane. So this is the epipolar line corresponding to X prime. Yeah, I hope you understand this. If there's a question, you're most welcome to ask. All right. Potential matches for X have to lie on the matching epipolar line. So if we want to now, this is X is an image of some capital X now in the 3D, the corresponding image is somewhere. So it can only lie anywhere on that epipolar line, nowhere else. So we don't have to search anywhere, but we have to search along only the epipolar line. Yeah. So it has to appear somewhere there. Potential matches X prime have to lie on the matching epipolar line XL. So if you know that, and we want to find the corresponding point to the other image, we only have to search along the corresponding epipolar line. Yeah. So let's see that in practice what has happened. So here some points of corners have been marked. Okay. Points of corners. The corresponding epipolar lines have also been given. These are the corresponding epipolar lines for those 4 points. Now, if you want to find the same point, this one here, how should you do this? We can search along this line. See, here we found it. We don't have to search along the image. How about this one? This corner, right? If you search along this line, see, here we find that. That's the thing. So take this for example. This is the corresponding epipolar line for this point. If you search along that line, that point is there, right? The top of that traffic sign or something. Yeah. So this is the thing about that. Okay. Whenever 2 points x and x prime lie on the matching epipolar lines L and L prime, the visual rays corresponding to them meet in space. That is, x and x prime could be the projection of the same 3D point. So one thing that we have to note is, if we take two lines in 3D, so two lines in 3D don't have to meet. See, they can be like that. They don't have to meet. See, they don't have to meet. Meeting is a special condition. They don't have to meet. Meeting is a special condition, right? So I hope that is clear to you. So that constraint uh, comes into the picture if these points are on the corresponding epipolar lines. See, remember in general, two rays do not meet in space. So a caveat, if x and x prime satisfy the epipolar constraint, it does not mean that they have to be projections of the same 3D point also, because x and x prime, capital X and capital X prime, can be along the rays far away also. Okay, so that thing is also there, but that's okay. Now let's look at how to obtain the essential matrix. That means mathematically capture this relationship that we physically saw. Yes. Okay. All right. So now consider this geometry. R is the rotation of the camera O prime with respect to camera O. So I hope now, because of the exercise that we did, you can understand that this camera, actually that camera we can draw like that. This is the camera, and that's the center of the lens of the camera. This is the center of the lens of the camera. So the second camera we can draw like something like this. That's the center of the lens. And you can see there is some rotation between the two cameras, right? That is what we are talking about. Rotation matrix. It's a 3 by 3 matrix, as you know. R is the rotation of the camera O prime with respect to camera O. T is the translation. It's a distance between the two camera centers of the camera O prime with respect to camera O. Assume the intrinsic and extrinsic parameters of the cameras are known. World coordinate system is set to the first camera. That means the first camera's rotation matrix is the identity matrix. Consider that for the time being. All right, now let's do some little bit of image taking. Then the projection matrices are given by K I0, K prime RT. Is that okay? Now for the first camera, we know that the rotation matrix, the identity matrix, and the translation is 0. Aligned with the world coordinate system, there is no translation. So only the K matters. For the second camera K prime, and there's a rotation R. So these are the P1 and P2, the camera matrices. These P1, these P2. So because you studied camera matrices, I hope that these are understood by you. So I will call it P and P prime, right? That's better. P and P prime. Okay. We can pre-multiply the projection matrices and the image points by inverse camera calibration matrices to get normalized image coordinates. So we can get normalized image coordinates, but if you pre-multiply with that, because we have to get rid of this camera calibration matrix, because we already have that. In this context, we are assuming that this K and K prime are available to us. So in the imaging geometry, because our imaging geometry camera action is what? So I will just write equal to, of course, you know that there's a scaling factor, is P capital X, right? That's how we make an image, and then we can expand it. X equals, yeah, K I for the first camera identity matrix, horizontal concatenation 0 and capital X, right? So we are taking this X is an intermediate matrix, taking K to the other side. So okay, by K inverse. So I hope you can see that. Then we get the normalized coordinates. Yeah. So now we have the normalized coordinates. These are found by I0x, as you can see here, and RTX. Yeah. TX. Okay. So X normalized is I0x. X prime normalized is RTX. I hope that is clear to you. If you have a question, of course, you are most welcome to ask. So now to clearly show that we will explicitly state using homogeneous coordinates that our capital X is like this, X and 1. So of course you know that X has the X component, Y component, and the Z component. Okay, it's there, but we are not writing that. So I0, X and 1. I hope this is clear to you. And for the second camera, we will have RTX1. So R multiplies X, T is there. So RX plus T. Yeah. Any questions about this? Okay, I hope these equations are okay for you. We have X prime equals RXT, and this means that the three vectors X prime, Rx, and T are linearly dependent. That's why we can write the vector X, right? This vector X that you can see in red, that has been able to be expressed as RXT. So that means this vector, and this vector must be, of course, linearly dependent. That's why you can write them in an equation, right? Linearly dependent. Uh, so this constraint can be written using the triple product. Do you understand? Remember the triple product. I hope you do. Maybe I will show you the triple product using Wikipedia or something. Yeah, triple product. Uh, do you remember this? So if you have a vector B here, vector C there, and vector A there, triple product is A dot B cross C. A dot B cross C. Maybe you remember from A levels. Okay. So I just wanted to show you that this is a familiar concept. So triple product thing is, I will draw that again. Uh, now, if you have a vector A, right? Vector A and another vector B and another vector C. Triple product means you can write A dot product B cross C. Between B and C, you have the, oh, I should not write it like that. So at least all the, I will do it again, no problem. So this is our C, this is our A, this is our B. So the triple product is C dot the vector A cross B. This is the triple product. So only thing that you need to remember is this one gives the volume of this parallelepiped. This is called a parallelepiped. This object, trapetia Barger, parallelepiped. It gives the volume of that. Volume of that. So if the vectors are linearly dependent, like so, that means the third vector is on the plane of the second vector. They are on the same plane. If they are on the same plane, this volume must be zero. So this gives a volume. If this gives a volume, the volume must be zero. So we can set it to zero if they are linearly dependent vectors. Yeah. This means that three vectors x, x prime, rx, and t are linearly dependent. This constraint can be written by the triple product. You can see the triple product they have set to zero. So t cross rx, x prime is zero. So I hope that this is clear to you now. Okay, then we can write this cross product as a matrix multiplication, this cross product, and using the so-called skew symmetric matrix. I will show that what that is. This is the skew symmetric matrix. So if you want to write a cross product as a matrix multiplication, which is easy, you can convert the elements of A like this to a skew symmetric matrix, and then you can write A x B as a matrix multiplication. So now you can see we have the constraint now. X prime transpose Ex is 0. What is E? E is the essential matrix. The form of E is TXR. TXR is E. That's the formula for our essential matrix. So when the camera calibration matrix, that means K and K prime are known, intrinsic camera calibration matrices, we have the essential matrix. What is the formula for the essential matrix? Tx times R. So if you have two corresponding points, x and x prime, x transpose Ex must be 0. E, as you can see, is a 3 by 3 matrix. 3 by 3 matrix. So we can see this is a 3 by 3 matrix, right? Yeah. So this is the essential matrix, very simple, and we just actually derived that. Ex is epipolar. Okay, now there are many things that are from that. So Ex is the epipolar line associated with x. So that I need to give you a little bit knowledge to understand that. Now that is this one. So think about a line like ax plus by plus c is equal to 0. That's a line. So you understand that, right? So if you take, you can write a line as y equals mx plus c. That's possible. But also you can write a line as ax plus by plus c equals 0 also. Similar thing, right? There is also a way of writing a line. Okay. Now you can see if I gather the parameters of the line, parameters of the line are A, B, and C. I can write it like this. A, B, C. Consider that as a vector. And I will collect X, Y, and 1 here. X, Y, and 1. Yeah. So this is equal to 0, right? So you can see if you have a line parameterized in this fashion, A with A, B, C, and a point is X, Y, 1, their dot product must be 0. Can you see that? This one we call it L, actually L transpose, because all row vectors we write as transpose, right? Of convenience, L transpose. You can see L transpose X is equal to 0. So look at this. Now we have X prime transpose Ex is equal to 0. That means, okay, this Ex must be a line on which x prime is. Remember, if there is a point on the line, if this is my L, and this is a point on the line, x, yeah, then my constraint is, so let me call it x prime, okay, x prime, and it's L prime, okay, x prime, I can write L prime, the symbol only, transpose x prime is equal to 0. I can write that. Of course, because transpose you can interchange, I can write x prime transpose L prime is also equal to 0. Both are okay. So what we are saying is this kind of a relationship here. We have x prime transpose and there is Ex here. Then our Ex must be this, right? Ex must be this. Ex must be L prime. So that's why we call that Ex is L prime. So if you know the essential matrix, we can compute the line on which x prime has to lie. Yeah. So this is very nice. Similarly, E transpose x prime is the epipolar line associated with x prime. That means L is equal to E transpose x prime. That also you can derive. So I will not further derive other relationships, but these are available if you want in the multiple view geometry book, which I showed you last time by Hartley and Rizaman, that book. I'll briefly show you a picture of that book. This book. You can see the picture of that book, right? All the details are in that book. It is freely available for you to download. It's a great book. Okay. So we will not go into further details about this. And then there are other things. E is equal to 0, E transpose E prime is equal to 0, E is singular rank 2.5 has 5 degrees of freedom. All these things we will not study now. So now we got a formula for the essential matrix. Then the fundamental matrix. If you know the essential matrix, understanding the fundamental matrix is very simple. Essential matrix is for the case where the intrinsic camera calibration matrix is K and K prime are known. When they are not known, we have the fundamental matrix. So the calibration matrix K and K prime of the two cameras are unknown. We can write the epipolar constraint in terms of the normalized coordinates. So remember, for the essential matrix computation, we use the normalized coordinates. So then we can write down the same formula. This is the same formula that we saw in the previous slide. X prime transpose Ex is 0. Now I'm specifically saying that these are the normalized coordinates. Actually, we use normalized coordinates. The formula for the normalized coordinates is you have to just multiply with K inverse dx. And X prime normalizes with K prime inverse, you multiply X prime. So these were things that we did before. So if we replace them, yeah, in this fashion, we have the fundamental matrix. So you can see these normalized ones, we replace with that, and this we replace with that, and then you will have the fundamental matrix. So fundamental matrix is K prime inverse transpose, unfortunately, E K inverse. So this is the fundamental formula of the fundamental matrix. You only need to understand. Yes, this is by Fogera and Hartley, those people. Okay, yes. So this is something that you have to remember. X prime transpose fx is 0. Is that clear for you? That means, like, if you know the elements of the fundamental matrix, and if you know corresponding points in the two images, you can see whether they are consistent. That means that they are the images of the same sort of point. There can be caveats. You have to get 0 if you do x prime transpose fx as 0. So fundamental matrix also has the same properties, similar properties as you saw for the essential matrix. I will not go through those details. Okay. So now let's briefly look at the estimation of the fundamental matrix. So what do you think? The fundamental matrix is a matrix that we obtain from the matching pairs of points x and x prime. So if you have these matching pairs of points like that, you can see they have obtained two images. So if this is let's call it x1, the first point, its matching point, we call, not matching actually, okay, this one, x1 prime, right? And this point and this point are matching points. So this is x2, let's say, and if that is the case, this is x2 prime. Like that, if you have matching points, okay, you can see they have put the multipolar geometry book also. I also had it when I was studying on my desk all the time because it's such an important book. Yeah. Given correspondences x and x prime, constraint x prime transpose fx equals 0, and you can write with actual elements of f in this fashion. And if you do the multiplication, you will see that f1 once multiplier, f11 gets multiplied by x1 prime, and then after that you get multiplied by x. So you can say x prime x, x prime x. F12 multiplies x prime y. F13 multiplies x prime, and so on. So these are the ones. So you can write an equation like that. It is equal to 0. So for 1 point correspondence, you get this. But this is not enough. You have to use many point correspondences. That's why they have put 3 dots there. And we call that U. And you want to find these elements of the F. An obvious solution is you put all zeros. If you put all zeros, you will get 0 as the result, right? So that is not what we want. So we want to, we have seen this kind of a solution before. We want to minimize UF squared with the constraint, the norm of F, the if you square and add these elements of F, the norm of F is equal to 1. So for this, the solution is, we have seen this kind of solution before, eigenvector of U transpose U with the smallest eigenvalue. So by using the SVD function in Python, NumPy, you can solve this. Yeah. And then there's a thing called enforcing the rank 2 constraints. We know it needs to be singular and rank 2. How do we enforce it to be singular? Solution take SVD of the initial estimate and throw out the smallest singular value. So you initialize like this and throw out this sigma 3. So this kind of thing you have to do. So these are practical things that you have to do. So you can see the initial F estimate. So the epipolar lines are not actually crossing because of this wrong estimates. And then when you do the rank 2 estimate, they are crossing at the same point. So then there's a thing called normalized 8-point algorithm. Recall that x, y, x prime, y prime are all pixel coordinates. For example, x can be, maybe x prime can be 1000. These are pixel coordinates, right? X can be 900. So when you multiply 1000 and 900, this is a large number. But this one is just 1000, right? So you can see very large numbers and small numbers are there in the same matrix. When you have that, these solutions are not so well conditioned. So see, they have written the orders of these numbers. So that's why it creates numerical instability. That's why it is important to normalize them. In each image, center the set of points at the origin and scale it so that the mean square distance between the origin and the points is 2 pixels. So these are things that Richard Hartley found. Use the 8-point algorithm to compute F for the normalized points, enforce a rank constraint. Transform fundamental matrix back to the original units using if T and T prime are the normalizing transformations of the two images, then the fundamental matrix is like that. So these kind of things are there in the fundamental matrix estimation. The non-linear estimation is there. Linear estimation, what we studied before, minimizes the sum of squared algebraic distances between xi prime and the epipolar lines fxi, or points xi and epipolar lines f transpose xi prime. Non-linear approach is also there. So rather than doing that, we can see the non-linear one. So you can see it minimizes the distance between sum of square geometric distances like this. So the distance to the epipolar lines it minimizes. Yeah, so you can see fxi is the epipolar line, right? F transpose xi is the epipolar line. Distance of the point to the epipolar line. That is a more meaningful distance. So you can minimize that. then those minimization, optimization algorithms are required to do that. But we don't do that. When you want to estimate the fundamental matrix, we just use formula function in OpenCV. So these are some results that they got to show the after estimation using the 8-point algorithm, the average pixel errors, and when you normalize, how about it, and normalize and least squares, how about it, which is the better one. Okay. So there's a 7-point algorithm was set up least square system with 7 pairs of measures and solve for null space 2 vectors using SVD and solve for polynomial equation to get the coefficients of linear combination of null space vectors that satisfy det F. So these are also possible, but I will not go into detail. Um, So from epipolar geometry to camera calibration, estimating the fundamental matrix known as weak calibration. If you know the calibration matrices of two cameras, we can estimate the essential matrix E. Of course, these are K prime and K. These are the intrinsic camera calibration matrices. The essential matrix gives us relative rotation and translation between the cameras or their extrinsic parameters. Alternatively, if we calibrate the calibration matrices are known, or in practice, if good initial guesses of intrinsic values are available, the 5-point algorithm can be used to estimate the relative camera pose. So you can see people have worked so much on doing this. And there's a thing called fundamental matrix song also. So it is that important. So you can go here and listen to the song if you like. So fundamental matrix is an important matrix. Yeah. That's the end of that. Right. So now we want to look at the structure from motion. That means uh, how do you obtain the 3D reconstruction? I will go through a part of those slides. If you have a question for a couple of minutes, you can please ask. Okay, then we can go through this structure from motion. Anyways, making a 3D reconstruction out of images was a thing that people wanted to do for a long time. So you can see in this image also, they are showing that this is a very old image. 3 people are looking at the 3 cameras, 4 cameras are looking at the same scene. So they are thinking about the 3D nature of that, right? So the concepts are known in the early days also. Okay, let's briefly look at an outline of what the structure for motion design looks like. So let's first of all define what the problem and understand what these so-called ambiguities are. Then we look at the affine structure for motion using a technique called factorization. I think this was invented by Professor Takio Kanade. Projective structure for motion, and briefly look at the important concept called bundle adjustment. And modern structure for motion pipeline, we briefly look at, did not discuss too many details. Okay. All right, let's recall calibration. So camera 1, camera 2, and camera 1, camera 2, and camera 3 are there. We do not know K1 R1 T1, K2 R2 T2, K3 R3 T3. But what we know is there is this scene. In that scene, there are these 6 points, many points, okay, many points. And these point matches we have found. that we know that these points are matching. All the red points are matching, and all the pink points are matching. That we know. Given a set of known 3D points seen by the camera, compute the camera parameters. And these 3D points are known, and the corresponding ones are known in the image. So then computing K1, R1, T1, K2, R2, T2, and so on is called the calibration. What is triangulation? In the triangulation, we know these parameters known K1, K1, R1, T1, K2, R2, T2, K3, R3, T3. That means the camera's location and the pose and the intrinsic parameters we know. Given the known cameras and projections of the same 3D point in two or more images, so we know that the points are corresponding. What is the 3D location of that point? Compute the 3D coordinates of that point. That is called triangulation. Okay. What is structure from motion? When both these are not known, we don't know the camera parameters. We do not know the 3D point, but only thing that we know is that these points are matching points. When you have point matches, of course, we can do point matches by running what? Running a shift feature measure, or in the modern settings, you can run super glue or something. You can do the point matches. So that is structure from motion. So to define properly, given m images of n fixed 3D points such that ignoring visibility, that means you can see there are m images. M images, that means m cameras. You can see this pi goes from 1 to n. These are the m cameras. Cameras. And n 3D points, these are 3D points. J stands for the jth 3D point. I stands for the ith camera. You can see this is the image of the jth point in the ith camera. Small xij is the image of the jth point in the ith camera. Problem estimate the M projection matrix is Pi and N 3D points Xj from the Mn correspondence Xij. This is the problem. So you can see a diagram also. So if you take xj, jth point, you can see x1j, small x1j, small x2j, small x3j. So this is there for all the points, all the n points. You know, all the n points. And from that, our task is to estimate the camera matrices as well as the 3D point. You know how to turn that off. So, but this has an intrinsic ambiguity. That ambiguity, okay, I will show that ambiguity with this so-called Necker cube. Okay, now watch for this for some time, and I will ask you a question. The question is this cube rotating clockwise or counterclockwise? Clockwise or counterclockwise? So can you please answer this question? If it is clockwise, you can type CW. If it is counterclockwise, you can type CCW. CW or CCW. CW or CCW. So please type the answers. Some people are saying CW. CW. Both One person is saying both. So only three people have responded. Four people have responded. Nice. Okay. So the answer is it is ambiguous. Okay. So I will show you why it is so. Thank you for the answers. Uh, Now, if you think that this is away from you, this point is away from you, it is clockwise. If you consider this point is away from you, it is clockwise. But if you consider this point is closest to you, it is counterclockwise. That this point is closest to you, it's counterclockwise. Depending on which point you consider closest to you, it is clockwise or counterclockwise. Okay, again, if you consider that this point is close to you, it is rotating clockwise. If you consider that this point is close to you, it is rotating counterclockwise. So I hope that is clear to you. So there is all, it's not, SFM problem is not uniquely solvable. Could actually happen in a fine structure for motion also. So sometimes here you can think that the cameras are here, and here you can think that the cameras are below. So like that, these kind of things happen. Yeah. So mathematically, I can show you why that can happen. If we scale the entire scene by a factor of k, okay, and at the same time scale the camera by matrix by factor 1 over k, the projection of the same points remain exactly the same. So the images remain exactly the same if you put a k here and 1 over k there. So think about this like this. Now you assume that you go to the US and you take a picture of the White House. Yeah, several pictures of the White House. But if I give you a replica of White House, a small mm, clay replica of White House, you can make the same images by keeping the camera close, right? So therefore, if you scale the image, scale the scene, and do something with the cameras, you can get the same image. So the images are the same, but the actual object is different. So therefore, you can see obtaining the 3D reconstruction means obtaining the actual object. No, that this is not unambiguously doable. There is an ambiguity. Yeah. But without the reference measurement, it is impossible to recover the absolute scale of a scene. That means we must have a meter rule or something. In general, if you transform the scene using a transformation Q, I mean, we don't have to consider that just there's a K here. Yeah, one no K. But it can be an invertible matrix, Q and Q inverse. Yeah. Q and apply the inverse transformation to the camera matrices, then the image observations do not change. So there is this ambiguity of the reconstruction. So again, if I want to show you pictorially, this is from the Hartnett Sisserman book. Now think about this. Now this Q has been transformed using some matrix. It's an affine transformation actually. It has become a trapeze. It has become a cube. Has become something. Yeah, it has become. But you can see the image locations here and here are the same. Image locations here and here are the same. How did they do that? They did that by moving the camera center away and doing some other things also. See? So two different objects give rise to the same images in the left image and the right image because we adjusted the camera. So this is that matrix Q. This matrix Q at work. Yes. So I hope you understand that there is this so-called projective ambiguity in the 3D reconstruction. So when you 3D reconstruct some this house image, so you get these kind of distortions because of that. So to get rid of these distortions, we must manually impose that this line must be perpendicular to that line. This line must be perpendicular to that line, because in the scene we know that they are perpendicular. By imposing those metric constraints, we can obtain a metric reconstruction up to a scale. The scale cannot be recovered. Yeah. So if we impose parallelism constraint, we can get a reconstruction up to an affine ambiguity. Okay, what I said was this here is wrong. It's not an affine transformation that has been done here. It's a projective transformation. I'm sorry about that. It was right there. So this is an affine one. So cube becomes rhomboid. If we impose parallelism constraints, we can get reconstruction up to an affine ambiguity using the so like so. So similarity ambiguity after reconstruction obeys orthogonality constraints. That means we know that the perpendicular lines on the camera parameters and scene. So then we can similarity up to a similarity ambiguity we can obtain that. Okay. So now let's define. We have finished defining the structure from motion problem. In summary, recovering the camera matrices as well as the 3D points given point correspondences. So let's see, using the so-called structure from motion, affine structure from motion, how can that be done using the so-called factorization method? Okay, so let's start with affine or weak perspective cameras. And these images can be obtained if you have a longer wavelength, longer focal length like that. So when focal length is short, you can see this line parallelism is seriously gone. But here the parallel lines are not, are just sort of parallel. So with that we can use affine structure of motion. So, but this kind of thing is called orthographic projection. You just get rid of one coordinate, z coordinate, just of the z coordinate in this case. So I'll let you observe that. So you can see with this matrix, yeah, z coordinate is just dropped, right? You are just getting rid of that. So general affine projection, a general affine projection is a 3 to 2D linear mapping plus translation. So mapping like so, and then there's a translation. So therefore, you can write that as AX plus translation. So this A is a 2 by 3 matrix. A1, A2 rows of the projection matrix. So we can call this row A1, this row A2 for convenience. So you can see these have a geometric meaning also. Okay. All right. So given M images of n fixed 3D points such that I goes from 1 to M. So this is affine camera, number of affine cameras that you have. This is the number of points that you have N. Problem is use Mn correspondences Xij to estimate M, projection matrix is Ai, and the translation vectors Ti, and N points Xj. Both the A, T, and X have to be estimated in structure from motion. The reconstruction is defined up to an arbitrary affine transformation, as we discussed earlier. That means if we get AT01 as the affine camera matrix, you can multiply it by Q inverse. If we get Xj and I, you can multiply by Q, because this Q is unknown to us. You need additional constraints for that. How many known and unknowns for M images and N points? Can you think about it? 3D points are not known, yeah. So that means capital X's are not known. That means XJs are not known. So if you take an XJ here, yeah, how many numbers are there in that? X coordinate, Y coordinate, and Z coordinate. So therefore, if you consider n of them, 3 times n unknowns are there, right? And then if you take M cameras, each camera has how many parameters? Remember from the previous slide, AI has 3 parameters, 6 parameters. here has 3 parameters, 9 parameters there. But there is an ambiguity. So 2mn nodes. So why do we call it 2mn? Because there are mn point by just two constraints are there, x coordinate and y coordinate, and 8m times 3n unknowns. I lied to you by saying 9. Uh, so this is the T1 and T2 and 6 parameters, right? 1, 2, 3, 4, 5, 6. I'm sorry about that. 8 parameters. So that's why we have 8m plus 3n unknowns. So we can actually, we know that number of equations must be greater than the number of unknowns, right? So we can have this constraint also. 2mn must be greater than 8m and 3n. So 12 fine ambiguity takes away 12 degrees of freedom. So that's why this minus 12 is here is required. Example 2 weaves, we need 4-point correspondences. We can do a small calculation. For 2 weaves, we need 4-point correspondences. I can substitute and show you. So 2 weaves means our m is 2. 4-point correspondence is n is 4. So this one is 2. So you can see 16 altogether, right? That must be greater than this. So 8m. So m is now here is 16. Yeah. 3n. N is 4. That means 12. So that's minus 12. So these two cancel off. So 16, right? This constraint is satisfied. Any questions about this? Okay. To do a fine structure, first center the data. So of course you have to subtract the mean of the points. Then you can substitute this, and then you can obtain this expression AIX J hat. After centering, each normalized 2D point x at ij is related to the 3D point by xij is equal to AIXJ. We can get rid of the need to center the 3D data and the translation ambiguity by defining the origin of the world coordinate system as a center of the 3D points. That kind of thing we can do. So, okay, now this is the most important part in this. You can see Tamasi and Kanade, Professor Kanade have discovered this. Let's create the 2m times n data measurement matrix. 2m times n data measurement matrix. So you can see x11, x12, x1n. Okay. So these are the points in horizontal direction. These are the 2m cameras. Due to cameras 2m because x and y coordinates, right? x21, x22, x2n, xm1, xm2, xmn. Yeah. I hope it is clear to you. So this is we can write as xij equals AIXJ, and you can see this is obtained by, so each point is obtained by AI times xi, right? The second one is obtained by A1 times x2, A1 times xn. So because of that, we can show that it is a multiplication between this matrix of 2m times 3 and this matrix 3 times n. In points, and each point has 3 coordinates, right? So they notice that this has 3 as the second index, this size, this has 3 as the number of rows. So it is essentially the multiplication between a 2m by 3 matrix and 3 by n matrix. It's a rank 3 process. So what must be the rank of the measurement matrix D? It must be rank 3. So why it is rank 3? Because we have multiplied with by a 3-column matrix and 3-row matrix. So we write it as M and S. Yeah, M and S. You can see M and S there. Then pictorially, this is a 2m by n matrix that must have been composed by a matrix of 3 columns and 3 rows. So we use the so-called singular value decomposition available in NumPy also. So 2m by n matrix, you will be 2m by n matrix. V transpose will be an n by n matrix. This will be an n by n matrix. So then what we do is, noticing that it is a rank 3 process, yeah, we only take the first 3 elements of that. This sigma is the sigma contains single values. It will contain only diagonal elements. All others will be 0. So it will contain n diagonal elements. From those n diagonal elements, we keep the three largest. That's how. So you keep the three columns here, three rows there. So now you can see up to some ambiguity, the camera matrices and the 3D coordinates can be recoverable up to now. This is the closest approximation of D with rank 3 matrix in terms of the so-called Frobenius norm. What to do about sigma 3? One solution is you can get the square root of that, getting the square root of EC, because these are just the diagonal elements, and combine to get M and S. So if we do this decomposition, one possible solution is that there are other solutions also. So you can have Q and Q inverse. Remember the ambiguity that we talked about. It can be there. So far we have obtained one solution, D equals 2n by 3 and 3 by m. Yeah, and if we want, we can obtain other solutions by inserting any invertible matrix, such that camera matrix A, I think, corresponds to orthogonic projection, that is, has orthonormal axes. So we impose that constraint. So that means this vector and this vector must be perpendicular. So we can impose that constraint. So this translates to 3m constraints on the 9 entries of Q. I will not think about that too much, but you can impose those constraints and obtain this I22 identity matrix. Are the constraints linear? First, solve for L. I didn't think about it. I will not answer that. Solve for L. Then recover Q from the Cholesky decomposition and update M to MQ, S to Q inverse S. If you like and if you want, next time I can show you a code. But we don't have to do that because OpenCV already has all these codes, but we can write step by step and obtain these also. Not very difficult to implement actually. If you follow the slides, you can implement them. Yeah, so this is the affine structure from motion and eliminating the affine ambiguity. I hope you understand the concept called the ambiguity. So you can see the reconstruction results that they have obtained. So those days, long time ago, okay, 1992, they have been able to obtain the point cloud of the corners of this little toy building, and you can clearly see that it's not a square. So ambiguity problem has been there. Okay. So dealing with missing data and so on, I will not discuss too much. So I like to end the structure from motion part here with affine, and then projective and so on are there. Then the projective structure from motion is there, and adding additional cameras and large scale one and so on. You can, I will not do, but please do some reading about that. So one of the latest papers in this, I have shown you this paper called VGGT, and that won the CVPR Best Paper Award. So it is that important. This area is that important. So this is you can see CVPR Best Paper Award means the best paper award in the topmost conference in the world. So you can see that they have used a deep learning scheme for that. So they can obtain the cameras, and they can obtain depth maps, they can obtain the point maps, and they can obtain the point correspondence all throughout. They can do that because of their knowledge of this structure from motion, this knowledge that we understood now. So you can see they are showing what their VGGT1 is. So you can see the 3D recons are beautiful, right? They are beautiful. These are very important for robotics and all these things, different scenes. That takes a little bit of time. Yeah, reconstruction. So Duster is also another paper. Pyramid. So Dust and Faster were the previous papers in 2024 and so on, I think. And VGGT is the 2025. CVPR conference happens in June. So people must be working on other improvements also. This so-called Duster. reconstruction. Using multiple images, you obtain the reconstruction. You can see when you have the reconstruction, you can rotate them and so on. That is the idea of that. So visualizations, you can see them. Is a Coliseum. Quite good, right? There are many other things that you need to get this kind of something like this working. Yeah. Okay. So that will conclude our geometry vision part. Mm. So let's take a break, and when we meet at 12:40, we will start looking at image classification. That part I want to start. I'll type a note somewhere. Let's pause the recording. If you have any question, please ask. Good afternoon, everyone. Welcome back. So we will study image classification from now on. So I will start with very basic classifiers, and I'll explain you what image classification means, and then slowly build up the knowledge for you to be able to understand and code deep learning based image classifiers. And then we will understand these very popular classifiers, how they work briefly. And then we will look at so-called object detection, that means drawing a bounding box also around these images, and then to understand how detectors like YOLO, early versions of YOLO work. Then there are many versions of YOLO, so all these things we cannot discuss in the class, but with the basic knowledge, I think you will be able to understand how they work also. Uh, then then we can discuss any topic that you want to discuss. There are current topics also, vision language models, image generation, all these things we can discuss depending on the interest that you have. So that is the classification to deep learning part. Mm. Then I had to briefly talk about image segmentation. That is the final topic that we want to discuss this class. So why? Uh, we look at the outline that we plan to do. You can see the 3D vision is the one that I completed now. Um, Now I'm starting with the introduction to deep learning and object detection and so on. So this one we will see how to do parallel segmentation part. Okay. So starting with the very simple ones. Briefly, a history about the deep convolutional networks. So 1950s, the perceptron was invented by Rosenblatt. I think it's a very famous story. Maybe you know that there is a New York Times paper article about this. Mm, um, I'll show you that. So this is that famous New York Times article. It's going to next page. Someone posted that. Shouldn't I click that? So this one. This person called Dr. Rosenblatt uh, talks about this perceptron thinking machine, uh, which was expected to read and write in a year with a budget of about $100,000. But you know that with the advent of ChatGPT and so on LLMs, now computers can read and write, but not at a cost of 100,000, but you can see billions of dollars have been spent, and it has taken about 1960, 70 years, right? So the service said, I think he worked for US Navy, it would use this the principle to build the first with perceptron thinking machines that will be able to read and write. It is expected to be finished in about a year at a cost of 100,000. You know, the Navy said the perceptron would be the first non-living mechanism capable of receiving recognition and identifying its surrounding without any human training or control. Yeah. The Navy revealed that the embryo of an electronic computer today that is expected will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So these are kind of dreams, I think. Yeah. Okay, so let's see what happened afterwards. 1950s, the neural nets perceptron invented by Dr. Rosenblatt. 80s, 90s, neural nets are popularized and abandoned as being interesting idea, but impossible to optimize, so unprincipled. Yes, I also thought so actually. Those days, I didn't have this kind of understanding. Those days, 1990s, Professor Jan LeCun achieved state-of-the-art performance on character recognition with convolutional networks. Main idea of today's the networks in generally, except the transformers, but a lot of researchers ignored him, especially in the computer vision. In 2000s, Hinton, Botu, Benjo, LeCun, and and other keep trying stuff with the deep networks, but without much traction or acclaim in computer vision. So computer vision community did not regard them. So some researchers do not still publish in computer vision, although it's the highest ranked area of publications. 2010 to 11, substantial progress in some areas, but vision community still unconvinced. Some neural network researchers got very angry at being ignored or rejected. In 2012, it shocked the whole world with this ECCB 2012 publication called the ImageNet Challenge publication called AlexNet. So I have shown the pictures of these authors, but I will show again. AlexNet authors. These are the authors of AlexNet. You can see here Ilya Sutskever, Alex Kisevsky is the first author, and he's the one who did the work, and this is Professor Jeffrey Hinton. After this work, the Turing Prize in 2019. 2019 Turing Prize was won by these three people, Joshua Bengio, Jeffrey Hinton, and Jan LeCun. I'm happy to say that my students have pictures with Joshua Bengio and Jan LeCun. And then finally, you know that Professor Jeffrey Hinton won the Nobel Prize for Physics. These are so great achievements. So, okay, so let's get back to what we want to do as image classification. If you have any question, you are most welcome to ask. Do not hesitate, actually. That's why we do the lecture live. You can ask any question, type a question in the chat, or you can just turn on the mic and ask. I'll be very happy. Actually, I'll be very much encouraged if you ask a question. All right, so image classification means now you input an image like this dog, it is a beautiful dog, and the output is to assign each image to one of the fixed categories. These categories are fixed. Cat category, dog category, deer category, bird category, car category, or truck category. We call them classes. So we assign this image to the dog class. That is the purpose. So now we see this as a dog, but what does a computer see? It sees a set of numbers, right? As you know, if for a grayscale image, it sees a 2D array of numbers. For a color image, it sees a 3D three planes of 2D arrays. Yeah. So this thing about what we see and what computer sees is called semantic gap. An image is just a big bit of numbers between 0 to 255. So example, 800 times 600 times 3 channels for RGB. So this is a very difficult task actually. And also there are challenges. You have to comprehend that these are truly challenges. Now we can ask to classify an image as a dog. That's okay, but there are so many viewpoint variations, right? So you can see maybe you are looking at the dog frontally in a frontal view, or looking at the dog this way. Yeah. So you can see because of the viewpoint of the camera, dog appears very differently. Intra-class variations. So you know that there are different types of dogs, right? Dogs, German Shepherds, Golden Retrievers, Pariah dogs, these types of dogs are there. And fine grained category. So that's what that means. So different, each class has different fine grained categories within that. And the background clutter. So you can see here the background, lot of background clutter. It is very difficult to isolate the three dogs in this with this background clutter. There are three dogs there. And illumination changes. You can see this is quite dark, but there is a dog here. And there are, and then deformation. So you can see here the dog, due to the posture of the dog sitting, standing, lying down, because of the deformations, and this is there. And then you can see the occlusions. So this dog is occluded by the fence, this is by the fence, and this is by due to this tablecloth or something. So those are called occlusions. So because of these reasons, image classification was very challenging, very challenging. Yeah. So image classification is the building block of object detection also. So object detection means not only you give a name to window in the image or a box, you draw that box also. You draw that box and give it a label, person. Yeah, you draw this box and give it a label, horse, like that. But if we have a mechanism of identifying what these important objects are, object areas are. What are the areas? What are the boxes that may have an objectness? Yeah, objectness. Then by taking them, we can feed it to an image classifier and get the class name. Object detection, and that is that one. And even for image captioning, this is important. So maybe if we know the class of the image, then we can write a caption to that image, a brief description of the image. Okay. Now, because of this, you cannot write a set of rules to identify dogs. Look for brown, look for. It is not possible to write set of rules and identify dogs. The possible way to do that is to come up with a machine learning approach. So unlike sorting a list of numbers, there is no obvious way to hard code the algorithm for recognizing a cat or other classes. We must go for a machine learning or data-driven approach. I hope you all agree with that one. So what we do is we collect a data set of images and labels. So they are labeled. That means every image will have a label. So like so, for example, this is from the so-called CFA10 dataset, airplanes. So each of these images we know is an airplane image. That means there are labels. These are automobile images, birds, cats, deers, dogs, frogs, horses, ships, and trucks. And this CFA10 dataset has 10 classes. That's why it's called CFA10. And each of these classes has, I think, 5,000 images. Yeah. So then use a machine learning to train the classifier. So we have the images and the labels, and we carry out a process called training. And after that process, we'll have a model, and which is a trained model. Then what we do is we use the test images which have no labels and the model to make a prediction, and then it will give you a label. So we have the model and give a name, image of a cat, and it will say it's a cat. So we will evaluate the classifier on new images. This is the paradigm that we use for image classification with training. Yeah. Okay, so we'll briefly look at the existing data sets first. So we will use these data sets um, for our exercises. First of all, this MNIST dataset. Actually, this dataset was has been created by Professor Jan Likund, because he did the handwritten check digit classification. Because of that, he collected for each digit, there are 10 digits, right? 0 to 9, I think 5,000 each. There's a data set. 10 classes, 0 to 9. These are 28 by 28 grayscale images, 50,000 training images, 10,000 test images. Results from MNIST often do not hold on complex data set now, but MNIST has been very, very useful. Yeah. So this is the CIFAR 10 dataset. I already spoke about the CIFAR 10 dataset. You can see it has 10 classes, 50,000 training images. That means 5,000 images per class, 10,000 testing images, 1,000 per class, and these are 32 by 32 RGB images. So when you consider 32 by 32 RGB, you know the 32 times 32 times 3, each of these images is a vector of size 3000 72. So these are 3072 dimensional. These are vectors 3072. But if you take 28 by 28 for MNIST, so 28 times 28 is equal to 784. So these are 784 dimensional vectors. This data set contains those vectors. Okay. Any questions about this? Is there a question? Okay. Move forward then. Okay, so this is CIFA 10, and then there's called CIFA 100 also. There are 100 classes, 50,000 training images, 500 per class, and 10,000 test images, and there are 100 images per class. These are also 32 by 32 RGB images. And they have 20 super classes also with 5 classes each. For example, if you take the aquatic animals, mammal superclass, it has a beaver, dolphin, otter, seal, and whale. Trees, maple, oak, palm, pine, willow. So the superclass thing is also there. So this is also useful for some tasks. Then ImageNet. This is one of the greatest contributions in computer vision. This was done by Professor Fei Fei Lee's group. Actually, she gives a TED talk about this. Professor Fei Fei Lee, and she cries in the TED talk because a lot of people have laughed at her when she tried to create an image that means a very large image database. It has that large number of classes, but the popular subset that we use is called the image large scale visual recognition challenge. But the subset that they use for that, it has 1,000 classes, about 1.3 million training images, about 1,300 per class, and 50,000 validation images, 50 per class, and 100,000 test images, 100 per class. So test labels are secret. Images have variable sizes, but often they are resized to 256 by 256. There is also a 22,000 category version of ImageNet, but less commonly used. So you can see flamingo, cock, like that. A lot of images are there of a lot of classes. Siamese cat, Persian cat, Egyptian cat, and so on. Okay, so then MIT places 365 classes of different scene types, approximately 8 million training images, 18,000 validation images, 28,000 test images. Images have variable sizes, often resized to 256 by 256. And then there's this Omniglot dataset is 1,623 categories, classes with 50 different alphabets. These are different alphabets. So 20 images per class meant to test few shot learning. Few shot learning means you have a classifier, you want to make that classifier work for you, or new dataset using only a few labeled images, few shot learning. Okay. So First of all, to understand a few concepts about this classification, we will look at nearest neighbor classifier. But before that, do you have any questions? Okay. Now, this nearest neighbor classifier is very easy. So this memorizes all data and labels, predicts the label of the most similar image. With n examples, how fast is training? Training does not take time because the examples have labels. So it is constant. We call it constant time. It does not spend time based on the number of training examples it has. With the train, how with n examples, how fast is testing? For testing, you have to check with each example in the class, in the data set. Okay. So this is bad. We can afford slow training, but we need fast testing. Okay. So let's look at this now in this image here. I'm showing three classes, the blue class, the orange class, and the green class. So these are the training images. They are classes we know. We know that this is green, this is green. We know that this is blue, 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 blue. And we know that this is orange, orange, orange. So with using some techniques, actually I have used nearest neighbor. I have drawn the boundaries between these classes. You can see these are the boundaries, right? Boundaries. How I did that, I will, we can understand later. But now our question is, when we get a new data point, that means this is new, its label we do not know. How do you find what its label is? Is there anyone who would want to suggest some method? Maybe you can type or we can turn on the mic and say, how do you find the label of the cross here? Whether, how can we decide whether the label of the cross is blue, orange, or green? Some people are answering by distance measurement. Some person say, yeah, that is correct. What are the other answers? Can we have some answers? Okay. I'll tell you the answer. Um, Now what we do is we compute the distance from this example of unknown class to all the training examples, to this one, 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 this one, this, and finally the distance to this one. So how many training examples are there in this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, n is equal to 10. N is equal to 10. Okay, there's no training required. But in the testing time, that means when we are trying to find out what the label of this cross is, how many distance calculations did we have to do? So can we have a number as the answer? How many distance calculations did we have to do to find the closest neighbor of that? Uh, from the cross to all other labeled examples or exemplars, we have to compute the distance. So that means we have to actually do 10 distance computations. That is correct. 10 distance computations is what you have to do. So you can see the number of computations that we have to do is in the order of 10. Order of 10. That means in this case, if you generalize, is in the order of n. So this is bad. So if you come after you compute these distances, you find the closest one. The closest one is actually this one, right? This is the closest one, and we take its class as the class of this one. So we will call it blue. We'll call it blue. Closest one's class is the class of that. So this is the so-called nearest neighbor. Its test time computation complexity is n. This is considered to be very bad because we have to go through all the training examples to find the class during test time. Yeah. So, but there are faster methods, but we will not talk about that here. Okay, so this is an actual slide which shows the nearest neighbors. Okay, so you can see they have found the nearest neighbors for this object, this object, this object, this object, and so on. So which ones are correct? Which ones are wrong? Nearest 10 neighbors they have found. This one seems to be correct, right? It is correct. This selected some other animal wrong. Wrong. Cat is correct. Some are correct, some are wrong. Okay, you can see these are wrong, and few of them are correct. Yeah, yeah. Can you see that? Yeah. All right. So this is the nearest neighbors thing. I hope that it is clear to you. All right. So now to compute this nearest neighbor, we wanted to calculate the distance. But if you are given images, how do you compute the distance? So in this case, the distance computation is very easy. Oh my goodness, I have the distance has gone, right? I forgot that. So here computing the distance is easy. So you can see we can take the coordinate here, x coordinate and y coordinate. Let's say this is 4 and this is 5 or something, right? And this one's the new one. New one is this one. This one's coordinate. Let's take this one is 8, and this one let's take it as 6. So how do you compute the distance? You can take 8 minus 4 x difference squared plus we can compute the y difference squared. It doesn't matter which one you subtract from which one. 6 minus 5 squared. So it's called Euclidean distance. Right? You can just square the individual coordinates and add them. Or you can, because you are lazy to square, you can just get this one also, right? 8 minus 4. You can take the, okay, negative values are bad, so therefore you have to take the positive value of that. Otherwise, the negatives and positives get cancelled off. 6 minus 5, we can get the modulus value. So these are different distance metrics. So here you will get uh, 16 times 117 is the distance here. Here you will get 4 plus 1, 5 is the distance. It does not matter usually, but of course, distance metric matters, but in this case, it doesn't matter too much. Mm. So that's how you compute the distance. In this two-dimensional case, it's very easy to find the distance. But if you go for an image like that, how do you find the distance between two images? You can individually subtract the pixel values, like so. So you see here, I have found I have drawn 1, 2, 3, 4. These are 4 by 4 grayscale images. 4 by 4 grayscale images. So the test image is this, training image is this, that is also 4 by 4 grayscale image. So you can subtract the individual elements. Yeah, these are you subtract individual elements. That means 56 minus 10 is 46. 32 minus 20 is 12. Like that, you just get the positive value though. If there's a negative value, you disregard negative value. For example, 0 minus 32 is minus 32. No, you disregard the negative sign and put 32 there, because otherwise the negatives and positives will cancel out. Then you add. So this is how you compute a distance metric, and this we call L1 distance, because we got the modulus value. Yeah. I hope you understand the distance metric. One of the distance metrics. There are problems with these distance metrics, that's for sure. Any questions? Okay. So now what I have plotted is the number of nearest neighbors that I consider to decide the class. For example, let's take k equals 1. K equals 1. Here you can see only the nearest neighbor matters. How can we um, decide that? For example, if you think this is the okay, this is the blue region. Okay, all right, this area is the blue region. You can clearly see that blue region. But because there is the orange one here, near that there's an orange region, right? Near that there's an orange region, because only the nearest neighbor is considered. Now, if you consider three nearest neighbors, although an orange one is there, because there are blue ones close by, this region belongs to the blue one. That is correct. But there is a problem here, right? There is a small island of orange there. Can you see that? Yes. But if you consider five nearest neighbors, so those problems are gone. But you can see the boundary gets smoother and smoother. You can see the boundary slightly wiggly in here, slightly wiggly there, but that wiggly nature is disappearing when you have large number of neighbors. Especially this is clear when you have k equals 7 or something like that. You can see. So smoothness increases, but this is important because we want to be correct during test time, not during training time. So during test time, you can imagine that suddenly a new example comes here and lands right at this location, right at this location. So what is the class of that? We will call it orange, right? Obviously, we can say it is wrong. So if the class lands exactly here, we will call it orange. It is wrong. But in this case, if a class lands exactly there, we will call it correctly blue. So when you have a larger k, your test time performance improves, but your training time, the training examples can be incorrectly classified. That is okay. So you can sacrifice some training error to better the testing error. This is called regularization. Okay. So I hope you understand, when you increase the k from 1 to 3 to 5 to 7, what happens? Any questions? Okay. Then we briefly look at the distance metric. So distance metric k equals 1, p equals 2. So k equals only nearest neighbor, p equals 2 means in this formula, we put p equals 2. So when you p equals 2, you get the Euclidean distance. And when you put p equals 1, you get the so-called Manhattan distance, so what we considered earlier in this computation. So you can see here, this is the distance, this is the Euclidean distance. Yeah. Okay. So the general formula is called the Minkowski distance, and thereby putting different values to p, you can obtain this. So how the distance goes, I am showing here. So whether you are moving in this direction, that direction, the distance goes equally. So here it's different from this way or that way. Okay. So these differences you can think about, and you can read a little bit more about the distance matrix also. So if you take this k nearest neighbor classifier, what are the hyperparameters that it has? That means parameters that are not related to the training set. Of course, you have to decide what k is, that you already saw. K we have to decide, and what is the best distance metric. So there are two things that we have to decide. The k number, like how many nearest neighbors do we use? The k is 1, 3, 5, and so on. You usually use odd numbers because then they can vote and pick the correct class. And the best distance maybe we want to use Euclidean distance, Manhattan distance, or any other complicated distance, any other slightly different distance. There are examples of hyperparameters. These are examples of hyperparameters, choices about our learning algorithm that don't learn from the training data. These are the hyperparameters. Choices about our learning algorithm that we don't learn from the training data. Instead, we set them at the start of the learning process. Yeah. So, for example, K, we set them at the start of the learning process. Uh, and so on. So, with the right choice of distance metric, we can apply K nearest neighbor to any type of data. That's a good thing about the K nearest neighbors. Okay. Then about now you saw in when we discussed about the data sets, I said training set, test set, validation set. So we have to understand that. We will understand that now. Okay. So we have to choose hyperparameters using something called a validation set. Now here you can see idea one, choose hyperparameters that work best for the data. That means you take training data. So what works best for the training data? Of course, k equals 1 works for the training data. Yeah, because the near to that green dot you call green, near to the orange dot you call orange. So therefore, that orange dot in the training set will be correctly classified. So, but this is very bad. Always works perfectly on the training data, but makes mistakes on the test data. Second idea, split the data into train set and test set. Choose the hyperparameters that work best on the test set. So hyperparameters are tested on the test set. Bad, no idea how the algorithm will perform on new data, because when you get a new data set, it's not this set that you are getting. We get a new test set, right? Someone will give you us new data. So we have no idea how the hyperparameters will work in the new data. So this is also a bad idea. Then this one, idea three, split the data into train, validation, and test. This is a good idea. Hyperparameters on the validation set. We compute the hyperparameter, that means k and so on. We find these in the validation set, and the test set you do not reveal in finding these hyperparameters. Test set is with the manager; they don't give it. So in one data set, you saw that in ImageNet, the labels of the test set is hidden or something, right? They said that. So that's what I'm saying here. So this is a good idea, but the best idea up to now is the so-called cross validation. There we divide the data set into folds: fold 1, fold 2, fold 3, fold 4, fold 5, fold okay, 6 fold is the test set. So we compute the hyperparameters with this fold here, and then interesting, compute with this fold, compute with this fold. So there are 5 ways that you can do that. So cross validation, split the data into folds, tie each fold as a validation, and average the results. Useful for small data sets, but unfortunately not used too frequently in deep learning. So the best hyperparameters you can find because different folds are there. Okay. Okay, so let's see now. This is called cross validation. So we will see how that has worked in the k-nearest neighbor. Each now in this case cross validation to select k, the parameter k. Remember, it can be 1, 5, 3, 7, and so on. 3, 5, and so on. So example 5-fold cross validation for the value of k. That what has happened. So you can see cross validation accuracy is given. Cross validation accuracy, when you average the accuracies over all the folds. So you can see when k is equal to 1 or something, accuracy is this much. And then, of course, they have plotted the standard deviation also. When k is equal to, I think, 7 or something, we have the best one somewhere here. The line goes through the mean, bars indicate the standard deviation. Seems that k equals 7 works best for this data set. So when the k is large also, or very large also, it performs badly. So that sweet spot you have to find using your validation set in the five-fold cross validation. Okay, so this is true even for not only for classification but also regression also. In the regression, we try to approximate the real valued function. In classification, we want to estimate the categorical data class of them. So there's a thing called universal approximation. That means if you, as the number of training samples go to infinity, the nearest neighbor can predict any function. So here you can see only one training sample is there. So what the nearest neighbor can predict is this one. So it also approximates the sine wave. Here, several data sets are there. From here to there, it will predict nearest neighbor this value. From here to there, this value. So this value, if you think about it, you will see that is the correct value. So when you see, when you increase the number of training examples, that means these black dots are the training examples, you can almost fully approximate that function. But there is a thing called curse of dimensionality. This is an important thing to think about. For uniform coverage of space, number of training points need to grow exponentially with the dimension. So these are dimension one dimensional data set. 5 points are there. So these are the nearest neighbor classification. So if you find any point here, you classify like that. So to cover this space, you need 5 points. If you have dimension 2, to cover that space, you need 25 data points. But if you three-dimension to cover that space, you would need 5 times 5 times 5, 125 data points. So when the dimensionality increases, the number of data points that are required to cover that space increases largely. So number of possible 32 by 32 binary images. This is 2 to the power of 32 by 32. That means 10 to the power 308. That's a massive, massive, massive number to fully cover that space. It is not possible to find samples like that. So k nearest neighbor on row pixels is seldom used, very slow at test time. Distance metrics on pixels are not informative. So nearest neighbor with convolutional nets, of course, work well. So here is an original image, and then these are all nearest neighbors. They have the equal distance, but they are very different, right? For example, the eyes and mouth have been covered of the girl. Here some halo thing has been introduced. Here the color tint, but they all three images have the same L2 distance from the left. So yeah, therefore you can see the distance metric is also possible. The ability to sample the whole space of data with training examples is a problem, and also the uh, distance metric is also a problem. So let's briefly summarize this. In image classification, we start with a training set of images and labels, and we must predict the labels on the test set. That concept we understood. Image classification is challenging due to the semantic gap. We need invariance to occlusion, deformation, lighting, interclass variation, and so on, which is so with the dog images. Image classification is a building block for other vision tasks like object detection and image captioning and so on. The k-nearest neighbor classifier predicts labels based on the nearest training example. Distance metric and the k distance metric and the k are the hyperparameters. Full stop is required here. Choose hyperparameters using the validation set. Only run on the test set once at the very end. Decision boundaries can be noisy, affected by the outliers. Instead of copying labels from nearest neighbor, the majority vote from k closest points is better. Using more neighbors helps smooth out the rough decision boundaries. So this is the first lesson that we want to do on image classification. Next time, we will run some of these algorithms and we will take images and we will understand how to construct a very simple linear classifier. I will explain you what a linear classifier is and use the so-called gradient descent to come up with a classifier. So we will understand gradient descent and so on the next week. So we have few minutes left. If you have questions, you are most welcome to ask. Otherwise, we can conclude the class now.